at Isaiah Superhero and at Sherbrooke University. His research focuses on aeroacoustics and bio-inspired aerodynamics using both high-fidelity simulations and artificial intelligence. I guess the topic of his presentation will be about the latter and I guess how it can be used for the former. So thanks again to Michael for giving this seminar, and the floor is yours.
Thanks. Thanks for the kind introduction, and thank you for the invitation to give this talk about so artificial intelligence, and here focused on CFD. As you can see, this work has been done with a lot of collaborations with Cerfax and Helios, which is a common research group between Isaiah Superhero and Cerfax in France, and other institutions like TU München, EPFL, and University of Sherbrooke. So today, why is so I think I've started this this research about artificial intelligence, let's say 6 or 7 years ago. Now I have 3 postdocs and 6 or 7 PhDs working on this. So I will give you a glimpse of what they do to have an overall picture, and I will focus on one particular technical details, which is how we can couple CFD with the AI. But throughout all this research, I think we always try to answer this very question you can see, which is how effective is AI when you try to couple it with computational fluid dynamics, CFD. As you may know, there are several ways to do AI, symbolic AI and machine learning, and all my research, at least for the moment, is on the machine learning side, as most work, I think, dedicated to AI today. And so when you are dealing with machine learning, mostly you are dealing with data-driven methods, basically to train neural networks, which is, I think, the main tool used today for machine learning. Of course, it's not the only one. You can do Gaussian processes, random forest, and other sort of machine learning. But most of my work is dedicated to using neural network at some point. So when you are saying you rely on the data-driven methods and you want to see how effective AI is for CFD, the next question that usually arises is why using data would be better than just solving the physical equations you have. And when you look at this question, it's in fact a very long debate from an old time, which you can try to answer by also looking at the very nature behind the data and equations. And in fact, it's still an open question today. Maybe we can just, before going to more technical detail related to CFD, just take a few minutes to look into it, because I think it's a fundamental question we should ask even before doing AI to physics. There is a huge hype with AI, a lot of funding, but it's always nice to try to have some ideas why we could do that and if it can actually help. So there are 2 main views about data and equations and their nature. You have a Pythagoras side, which basically say equations are the language of nature. So equations are the very core of physics, and data are just a byproduct of this. And people on the other side usually rely mostly on theory and mathematics. On the other side, you have more the Aristotle view. Maybe Plato is not so far, which basically is the opposite, saying math and equations, they are just the language of humans to understand nature. And in that context, we could say that data are more fundamental and equations are just here to help humans to interpret them. I think people there are mostly doing experiments because even if today we are data-driven methods, we are thinking about AI, but for a very long time data was mostly associated with experiments. It's nice also to make the connection between AI and experiment, maybe both of them, they share the same way to produce results, which is a kind of inductive method. Basically, like from input and outputs of an experiment, you try to infer some rules. And these rules, by nature, they are a kind of statistical form. They never be completely certain. So the only thing you can tell with this kind of inductive method at the end is like the rule you get is kind of the most probable way to make a relationship between input and output, depending on the one you get. It cannot tell you for sure that, for example, an output is not going to happen just because it was not there in your data set at the very beginning. So the second view clearly opens the path to generalization. Like you base everything on the data you have and your lack of generalization. Between these two views, I really like to usually illustrate this with this example about Galileo Galilei. You know, this very famous law he produced in 1604, which is basically all bodies fall at the same speed, of course in vacuum. And when you think about this law, this physical law, for which you can make an equation, he was able to produce the law without any data. Like there was no good experimental data available so far. Like vacuum was still in a concept with a lot of debates. There were poor measurements. Even though if you have measurements and so on, this law, which is remarkably true, in fact, you cannot observe this law on Earth, because as soon as you have no vacuum, you always have friction somewhere. And it's first thing that we need to understand is, like, of course, data is not everything. Physical equations, as you can see in this very example, if you have all the data of just objects that you try to fall, you never get this law made by Galileo Galilei, because always hidden in the data you have friction effects. Yet this law it's very simple, and I think it can bring a lot of understanding on some motions. So you always have this trade-off, I guess, between predictions and understanding when you do physics. And probably using data, you can make predictions. I think it will be much more difficult to have profound understanding of physics just using data. And when you look at the work of Galileo Galilei, typically he wrote these books, the Essayer, in 1623, and this is typically what he said. He says that so philosophy for him is nature, is written in this grand book that it means the universe. He said like it is written in language of mathematics, and one important word which is in red here, he said that it's language of mathematics. Is you need to understand this math, so equation basically. Otherwise, it's humanly impossible to understand a single word, so not able to understand physics. So for him, clearly, equations are needed to understand physics, at least for humans. And the thing is, what about computers? Because what I will talk today is like computational fluid dynamics, so everything is on computer, and we know that putting equations on a computer is not that easy. You need to discretize things, you need to compute gradients. In that context, maybe data can help a lot. And in fact, when you look at artificial intelligence, it turns out like it emerged first in science where no or little mathematics exists, typically computer vision. If you want to detect objects in ideal images, for example, a cycle is very easy, but as soon as you have a noisy images, it's much more difficult. It's the same for robotics. If you try to make a robot walk, or in medicine, if you try to detect a cancer, there is no equations for medicine. And so data-driven methods that bring a lot, mostly because there was not so much effective methods that can already be applied. Typically detecting cancer is just you take the eye and you try to look if you see something. And I think data and data-driven methods they were really game-changing. So if you put everything together for the moment, at least my point of view on this is like artificial intelligence and data-driven methods. I think they will mostly link to trying to predict or to detect things, either in experiment or in CFD, rather than using understanding. And usually understanding is what you do next by doing low order models, try to interpret things. Maybe this is something that will come with explainable AI, these kind of things. Now we have also some new tools to make system identification that can be explainable, to do some physics. There are very recent work on unsteady aerodynamics, for example, from Brunton, which is in this kind of vein, but it's still very new, and most of the work on artificial intelligence using data for the moment, they are really more on the predicting and detecting side. Here, these are some simulation we do in my research group. Just to say, like when you have general equations, CFD is just producing a lot of data, and all these data, they are very case dependent. I think it's the main difference maybe between the equation and the data. Equations, they are very simple, very general. You can apply it to many things, here from an airfoil to a drone to transonic flows. Of course, it's not here with the incompressibility equation. And when you produce CFD, you get a lot of data which are case depending on the operating condition as well as the binary conditions, and so on and so on. And so for sure, when you will apply artificial intelligence to this data, compared to equation, you will have to look at their generalization capabilities. And we will see, like in a few slides, I'll try to put some challenges in AI when you do physics and CFD, and clearly generalization is a key. If you have to redo everything again, to rebuild data sets, to retrain neural networks, you lose too much on the way, and you really need to find methods now which are able to generalize well. If you look at CFD to try to have a guess of how AI can help specifically doing CFD, if you take just an example, which is a simulation of a 3D airfoil for aerodynamics, usually the simulation framework, CFD codes, they use a large computational domain, 10, 20 times the object size, just to put the boundary condition as far as possible. You use unsteady even when you want just steady solutions, because you want to be more precise. You need small time step and small cell size just because of the numerical schemes. You need all variables because you need to compute these equations which link all these variables, velocity, pressure, temperature, even if at the end you just want pressure or something like this. You need to compute on the whole volume, even if at the end you just want the pressure on the object surface. And as I tried to mention, like as an equation, most of the CFD codes, they are able to do almost everything. So it's irrelevant if you do a car, a plane, an engine. You use more or less the same kind of numerics at some point. I think it's a main difference when we think now about how AI can help doing CFD. It can cope more with the objective of what you want from a simulation. First, it was the simulation frameworks, that is the requirements you need, but your objectives, they are usually very different compared to these requirements. Most of the time, you try to have something dedicated to a few products. Typically, on my research, I do mostly airfoils or bio-inspired wings, maybe some cavities for aeroacoustics, but it's always more or less the same geometry. And again, when you look at the objective you want, it's quite rare. Maybe not when you really try to understand a new physics, but when you just want to design or to predict things, you just need like global quantity 0D, or sometimes 1D, like a pressure profile or something like this, and you don't need to have all your pressure, temperature, velocity everywhere. It means like AI can help by, based on this CFD, where you have everything, at least the natural thing is to just build surrogate models which are dedicated to a few products, just give you 0D or 1D data, and so on and so on. This is, I think, the typical way to do artificial intelligence. I will try to show you that, of course, is not restricted to that, and we can do much more. So typically, if you look at code or CFD code, I think this is more or less the roadmap or sketch of it. You go from inputs, which can be as a geometries or operating condition. So all you need to start the simulations. You have most of the case, a discretization part, so basically a mesh. You have all the numerics and your models. And if you're in an unsteady CFD, the goal is to produce the next time step so that at the end, you can have the whole flow, either steady or unsteady, and make a post-processing to have this final objectives that I just mentioned, which is sometimes just 0D. I just want the lift of the whole aircraft, or just the drag of the whole aircraft, or just the pressure distribution of the wing, this kind of things. So first, I think it's important to make clear that most of the time there is a huge difference between the objective of the simulations and what you need, in fact, to compute this flow. And in this roadmap, in fact, you can find a lot of ways where AI can help in doing this CFD, and you will see it's not just doing surrogate models. I will try to illustrate this with some current work done by PhDs and postdocs. So if we go through this roadmap, for example, we have like a Gen Wei, which is a PhD in collaboration with EPFL in Switzerland, where he has a work dedicated to just using artificial intelligence to manipulate geometries and meshes. You have, for example, here an example where we can generate in a few seconds a mesh, for example, is for the moment is restricted to 2D cases. But however, it's very flexible in terms of mesh type, mesh size, and so on. So you can do triangles, you can do conformal mesh or non-conformal mesh, almost everything with the same framework in a second without needing any retraining when you go from one shape to another. If we keep on going through this roadmap of doing CFD, and this is, I will focus my point today on this, is looking at some models or some sub-models of your whole CFD, the work of Eki Ajoria, Xingtong Chen, and Lionel Chen. There are three PhDs that looked at solving some PDEs, typically Poisson or Helmholtz equation, in a very fast way. And what you can see here, for example, is a flow for which the Poisson equation is computed by your neural networks, typically. And I will take this example to give you some details about what we can do, how we should adapt all the neural networks that are done, for example, in computer vision, and what you should do to be able to do this kind of CFD, because you cannot use them directly. Like, you always have to adapt to your problems because of all of the reasons we already mentioned, like CFD or a lot of millions of cells, which is not what people are usually doing with neural networks. We are using unstructured data, where most of the neural networks, they are based for structured data, and so on and so on. This work, this is what we do, but I wanted also to mention that, of course, AI can also bring new way to do CFD. Maybe you are already aware of all the works that follow PIN, so Physics Informed Neural Network from RACI, where basically, instead of discretizing the equations, now you have possibility to have a continuous solution of PDEs, and you are able to do that because of automatic differentiation. Which is clearly a different way to do CFD, even for the moment is still for simple cases. But typically it means, like, when you have trained your network on a case, then you can sample in time or space as you want. You can go to coarse or fine grids almost automatically without needing to compute something again, because the solution you have behind are continuous function instead of discretized function on a mesh. Of course, there are a lot of work on models, so I didn't mention them all here, but you have a lot of things related to turbulence model. At Surfax, there are also people working on combustion models, these kind of things, wall of the law, all these things that can help by putting more complex models, usually like based on neural networks, to improve the accuracy of CFD. Another work that we try to do is also to look at how we can predict directly, like to remove part of the solver and just predict directly the next snapshot, compared to what we have seen before, where it was an example of the Poisson equation, where there was still a classical time marching techniques to get to the next sample. Here, everything is done by neural networks. So you have, for example, an example here of the PhD of Antonio Alguacil, which is doing here some surrogate models of CFD to compute acoustic wave propagations in complex media, for example, here with a nacelle, so with the interaction with objects, with diffraction, and so on. It's despite all what we can do with this kind of results, it's also this work a very nice toy model to also look at how we need to adapt neural networks for CFD. Typically, like a lot of questions arise, like how you impose boundary condition in a neural network, how you can generalize a neural network, how you can, when a neural network is trained, how you can enforce some physical law afterward, so a posteriori. Or some ideas we can try to work on this surrogate model of acoustic wave propagation. And of course, as I mentioned earlier, you have many works related to just doing surrogate models. So going from inputs to the results is clearly the fastest way. If you want to really accelerate CFD, you just remove CFD. You take CFD data just to train a network to output what you need, typically 0D, 1D data. Here you have an example. It's a 2D field of a temperature field into a rocket engine, for which we can parameterize whatever operating condition and geometry, and we can output some global quantities and temperature fields. And when you have this, of course, comes many things. It's a very cheap way to produce results. You can do UQ analysis, so uncertainty quantifications. You can do shaped optimization. This is what we have done, for example, in that case, where we have obtained some Pareto front, which were very difficult to get with just classical optimization. You can do also system identification, trying to, based on some results, identify like input parameters. For example, we have seen this quite recently with where people try, based on CFD, to get parameters underlying roughness on a roughness boundary at a wall. So you see, you have many ways to apply artificial intelligence. The last one, when you have results, of course, is you can, since let's say my background is on instabilities, what you can do also with AI is, of course, trying to control the system with flow control. We have like a PhD, Brice Martin, and a postdoc, Sandrine Berger, which have dedicated work on that. It's a very specific way to do artificial intelligence, which is called reinforcement learning. And you have an example here, for example, where like reinforcement learning here is coupled to a CFD solver, StarCCM+, and this is AI, which is controlling this airflow to a target objective. It can be a location, it can be minimizing an energy, these kind of things. So about the key challenges that you can see and it was well introduced into this review from Brunton, Bernd Noack, Petros Koumoutstakos, and so on. As we said, like compare with classical tools, machine learning algorithm, they often come without any guarantees in terms of performance, robustness, generalization, convergence, even for a very well-defined task. I think it's a crucial point to be able to get more mature ML algorithms that can enforce this performance and robustness, to have typically user-defined error levels and this kind of thing. So I will try to give you some possible paths, at least the path we tried to go in that direction. The second challenge is how you can incorporate physics. Pin networks is a way, but like as I said, is also how you can enforce boundary conditions on your networks to be sure that your CFD or the surrogate models you have, they satisfy this boundary condition properly. For example, in the case of the acoustic wave propagation, you need to be sure that you have no waves that can go through your obstacles. Since you have just learned this, you can just hope that everything goes well. But in practice, usually you need to find methods to reinforce this physics at walls if you want to have precise results and not diverging results in time. And the next challenge, of course, is I think it's important to notice that everything we do in CFD are very different compared to most of what's done in AI literature. And we always have to adapt things, to rediscover things. What are the architecture we need, how we need to train, what matters for CFD and for fluids, which is typically a problem in fluid flows when we have multi-scale in space, so multi-spatial scales, multi-temporal scales. We need to be very precise. So all of this has to be renewed when you just take classical AI framework. So again, on the case I will show you, I will try to give you some paths and some ideas about this. So here is a glimpse or an overview of what we do in my research group. Of course, I will not go through everything. I will just focus on two, which is coupling a CFD solver with artificial intelligence, so typically neural networks. But this is what we have go through this roadmap. So time-space propagations that we use also to better understand how neural networks work, typically with boundary conditions, accumulation of error in time, these kind of things. A lot of things linked to generation of simulations or surrogate modeling in the hope to get very fast results to go to UQ, shape optimization, and so on. A topic which is not related to CFD, but with experiments, where you have a lot of inverse problems that are very interesting to look at through artificial intelligence. And as I said, also everything related to optimal control, which again is usually artificial intelligence, which are very specific. So reinforcement learning, you have neural networks into reinforcement learning, but it's a very different way to train these neural networks because it's neither supervised or unsupervised. So I propose that we go here during questions. If you want to go through some of these examples, of course we can. So about this work, we will focus here on trying to accelerate an incompressible solver. It's typically a work which follows the very well-known paper from Thomson that you can see here in 5, produced at ICML. So when you look at incompressible flows, the way it's done when you do the CFD is like you split you split the method into two. First, you make the advection of your quantity. So typically you have velocity at the previous time step. You just use your momentum conservation equation to get a new velocity u star, which of course does not satisfy the mass conservation equation because you didn't use this one yet. So to enforce mass, you combine mass and momentum conservation laws, and you end up with a Poisson equation, which reads like this. So typically, U star is not satisfying divergence of U equal to 0. And to produce a corrected velocity, you have to get this pressure here through the Poisson equations. Laplace of pressure is equal to a source term which depends on this non-null divergence of the velocity field. And so once you have the gradients, you can make the corrections of the velocity field, and this new time step can go back in the loop, and then you can time march your CFD solver. These Poisson equations, like the traditional way to do that is to use iterative method. The most simple one is a Jacobi method, but of course you have many work that have been done trying to improve these methods. You have a conjugate gradient, preconditional conjugate gradients, multi-green methods. So you have a lot of them. In the work I will show you, usually we stick with Jacobi methods, mostly because we also need to find some methods that work on GPUs, because AI mostly work on GPUs. But it's the same with all the methods. It's iterative, so basically the more iteration you do, the more precision you get, but the higher computational cost you have. And for all the CFD codes we tried so far, so either MantaFlow, which is the solver developed by the Tueres group, which is a group dedicated to also AI for fluid flows in TU München, or more HPC codes, so typically YELS2 or OpenFOAM or all these codes. At the end, when you look at a CFD, you spend almost between 60 and 80% of your time just to compute this Poisson equation. So you spend a lot of time to do that. So of course, the goal that was proposed by Thomson is just to replace this classical Poisson equation by a convolutional neural network. And then when you do that, the questions that arise come from the challenges I've already mentioned, which is how you can guarantee that the error over time is the one you want as a user. So to guarantee a user-defined error level, and also to get some insight about how you should build this convolutional neural network, or to train this convolutional neural network to minimize the error of such a code. So in the work we do, we do on purpose, we keep on purpose exactly the same kind of data set that have been done by Thomson. I will explain why after. So we keep the same, like, so the data sets, they are no viscosity, so it's just Euler equation in 2D or 3D. I will show you also 3D results after this. So it really looks like this. It's very simple flows. There is no air force, there is nothing. It's just random geometries with some random initialization. Basically, you just kick the flows to make it move. And you do like a couple of hundred of simulations, and you store some type step. So here in this database, we have like 20,000 samples. Since when it's unsteady, you can of course collect more data. So the data set is very simple. So no viscosity, infinite Reynolds numbers. There is no density variations. Very simple, and low resolution as well. So what we will do first is we will just train several architecture of neural networks. So I'm not going to introduce this architecture. If you need more details, you can really look at the classical AI book for convolutional neural networks. Typically, we have three kind of networks. The first one is called monoscale. It's just classical feed forward. So you connect convolution blocks one after the other to produce the output. And as inputs, you have one which is objects, and the other one is what you need for the Poisson equation. So this is a source term, so typically the divergence of your uncorrected velocity field, and what you try to get is a pressure field at the end. So here monoscale is completely straightforward. Multiscale is a way to look at different scales in the flow. So what you do is, instead of just looking at the classical inputs, you also downsample your inputs by a factor 2, a factor 4, and so on. And so you have new inputs where, like, you go from one branch to another, the resolution is decreased. If you have 128 for your input pixels, then you are just 64 for the second branch and 32 for the third, and so on and so on. And this has been done by people from AI in a computer vision to keep the details of the very large structure, because neural networks, they try to look at very small details like pixels, and sometimes they lost some very large scales. So these multi-scale networks, they have been designed to look at the several scales of the image, which is typically what we expect from a flow when you have multi-scales. And UNet is typically the same, where you look at several scales. It's just like you arrange the scales in a different way. When you look basically at this different architecture, we tried either to fix the number of parameters. So these are still small neural networks. In artificial intelligence, you can see 100 of millions of parameters now that has to be tuned. Since here we want to accelerate a CFD solver, we have to keep the networks small. So for example, here, like, the largest we have is 400,000. We tried also reduced one to see, like, on the same architecture, how changing the number of parameters change the accuracy and the predictions. And for UNet, I will present specifically, but we try now not just to change the number of parameters, but really to look at specific features of UNet, which are like the number of branches, so the number of layers that you have, the number of scales that is going to see, and receptive fields, which is a characteristics of convolutional neural networks. And so the questions that we will go through is if we can have some answers about how general these neural networks are, so how accurate typically on new cases, and we will try to find a way to quantify clearly what a new case is, how general a neural network can be, how precise they can be, and at the end, how fast they can be, since we want to accelerate here an incompressible solver. So to answer the first questions, once it's trained, all these architectures, what we do is just we evaluate on a very different case. Like you have seen, the one training example is something very basic. So here we'll do a plum case, where it's basically you take a box, you inject some fluids here at the bottom with a density which is different compared to the density you have in the box. And this problem is controlled by the Richardson numbers you have here highlighted in green. The Richardson number typically look at the ratio between the buoyancy and the flow shear effects. And everything else, the Reynolds number and the density ratios, they will not vary. The Reynolds number here, we are still invested. So we are still using the Euler equations. So this is the same as the training data set. Density ratio is kept low because we have a Boussinesq approximation. And again, as a reminder, the data set is also done at infinite Reynolds number, but a Richardson number, which is equal to 0, because there were no density variation in the flow. And so Richardson number is used here as a parameter to control the generalization, or how far the new simulation is from the training data set. It's simple if we have this Richardson number, which is a single parameter going from the data set to this simulation. So let's look at some examples. So if you take a lower Richardson number, so close to the data set, the training data set, you have on the left a CFD simulations in 2D done with the Shakopee method, and on the right the neural network. At first you can see that it's able to to replicate quite nicely this flow development of the plumb. You can see a very small inaccuracy there, but it's still very low, so you have a very small asymmetry of the flow. But still, you can say that for Richardson equals 0, it seems okay. If you want something more precise and more physical, you can look at, instead of just looking at this this flow coming up, like you can really trying to track this head position. So typically the highest point of the plumb, and to track it in time. So it's not a normalized time here and a normalized head position here for the neural network in black and the Jacobi solver here. If you increase the number of iterations of the Jacobi solver, you are not going too far from here. It's more or less converged here. However, you can see that when you go to lower number of iterations, of course, you have a large discrepancies of the Jacobi method. So basically, we can say, like in terms of accuracy, neural networks, they are here more or less the same as the Jacobi 200, at least for these neural networks. So now that we can compare the accuracy, let's look at the performance. Since we want to accelerate the CFD solver, we will just look at how fast it goes when you have a neural network, and you have the table here. This middle of my screen. So you have these two columns, the time versus the time of the neural network. So it's the time spent by the methods compared to the neural networks. That's why you have 1 here, because you compare neural networks with itself. So this is just to compute the Poisson equation. And this is the time you need for the Poisson equation compared to the total time of the iteration for the method you have. So typically what this table means is, like, of course, when you have Jacobi 28, which is quite inaccurate, the time is still quite large compared to networks, but the total time you need to solve the Poisson equation is still 30% of the total iteration of the solver. So Poisson equation is not driving everything there. However, as soon as you try to have something more accurate, so typically J100 or J200, so these two rows here, you go now to a time to compute the Poisson solver, which is now quite large. It's almost 64 or almost 80 here percent of the time you need to compute a whole iteration. When you look now at the neural network, which is in terms of accuracy very similar to the neural network, you can see that now this time is reduced to 2%. And so another way to say that is that the Jacobi 200 for the same accuracy is 250 times slower than these neural networks. So it's a huge gap. Of course, you always have to be careful with such results, because we know Jacobi is not the most effective way to compute Poisson solvers. So you will see also we have some results with a more classical CG method and so on. But still, we have a large enough gap to still think that there are some improvement possible. And neural networks here was not so much optimized, so there are still a lot of things to optimize, and we can in fact reduce still a lot this 2% to even reduce this. The other way is also to say, like, maybe 2% now of the total iteration, there is no need of further improving this performance, so we can also maybe do a larger neural network. So this number 2% goes to maybe 5 or 10%. It will not change a lot the time needed to compute the whole iteration, but however, if you have a larger neural networks, you can have something more complex, and maybe you can improve further this accuracy you get, or the generalization capabilities and so on. So here everything is done on this low Richardson number. Let's try to see now what happens when you try to generalize to a larger Reynolds number, which correspond to flow which are further away from your training data set. And this is what happens. So Jacobi 28, as always, is quite inaccurate, but still you have something which is kind of coherent in terms of flow structures. Jacobi 100 or 200 is here in the middle. And on the left, you have the neural networks, where now you can see a discrepancy which is an error produced by the neural networks because of a generalization problem. So this is a key challenge that you need to fight if you want that your method is able to generalize well, if you want a reliable solver that you can give to someone to say, like, you can be confident on this solver, even if you have a neural network, it will produce something physical at the end. You clearly need to find this, to fight this. And if you go even further in terms of Richardson number, typically here 37, but we can go up to that. You can see through time here a comparison between Jacobi 200 and the neural networks. And here, like, it's not just that we are inaccurate, but the neural networks coupled to the CFD solver is even completely unstable. As you can see here, we have a loss of symmetry, so everything goes wrong. So now the thing is how you can do an AI-based solver which is robust to this, which is able to generalize. Of course, you can improve the learning, you can change the loss functions, the architecture of the network. As I see, like, as I mentioned, like, we have 2% of time just spent for the neural network, so you can maybe have a larger neural networks. We can also improve the database with more cases, more Reynolds number, more Richardson numbers as well. The main problem of this is, like, you will always have limits. If you increase the database, if you try to improve the learning, it will always come to a point where some flows will be outside of your training data set, and then you will not have any guarantee of the error. So the strategy we propose instead is to hybridize deep learning, so the neural network with the CFD. In fact, it's a very simple idea. When your neural networks infer a solution, so typically pressure gradients, then you can make a correction to get the velocity. You can compute the divergence of the velocity. And since you have an equation here now, which is the divergence of the velocity, you can now just look at the error that your neural network is doing. Like, it's, since you have a residual of an equation, it's supposed to be 0. It's like an unsupervised task. And so you can actually, in the fly, look at this error, and depending on a user-defined threshold, here epsilon, either the error is below this threshold and you go to the next step, or it's larger to this threshold and you use a classical Poisson solver to iterate, and you just use these neural networks as an initial guess for this traditional solver. For the moment, we use Jacobi solver because it works as a Newton algorithm. So we know that it will mostly depend on the initial guess you give. For CG method and other things, probably we need to find a new way to hybridize CFD and DL, because for CG method, it's not just the initial guess that you need. Like, the better is to provide a more accurate preconditioner or this kind of things. So for the moment, I will just show result for Jacobi for the Jacobi solver. And this is what happens when we do this hybridization. So now with the same Richardson numbers 37, the one we have seen which was completely unstable, now just by doing this, we have a stable code. Of course, because after the neural networks, the classical methods, which is much more reliable, are giving you results. But the thing you have to look at now is if you have used a classical method at some point, have you lose everything or not in terms of performances? And when you can see here is like the hybrid methods, the time to compute an iteration of the hybrid methods compared to the neural networks that we have seen before, which were already very low. In fact, the additional time you need is almost nothing. It's 5% of something which is already very, very small. So at the end, what you get is you have a CFD solver which is coupled with coupled to your neural networks, for which you have here a guarantee of the error made because you have the hybridization, but still with the performance we have seen. So typically, the Poisson solver now is just 2 or 3% of your whole iteration time. If we keep on going on how fast they can be, the next step is to evaluate the several networks that I've introduced in terms of architectures. So we have several, three networks I've introduced: a monoscale and the multiscales, and two multiscales with different kind of parameters, and we compare to Jacobi methods. Here you have the plot of the iteration in time compared to the Jacobi iteration you need in this hybridization. So of course, when you have just Jacobi itself, which is running, so you see that you need 200 or more iterations to converge, which is consistent with what I've said at the very beginning, like a J200 is sufficient to have something converged. However, as soon as you go to neural networks, you can see that you are able to reduce this number of Jacobi iteration. Monoscale is not working so much. It's a triangle here. You are reducing it, but by a factor 2 or not so much. However, like the multiscale network is really working well. In fact, the multiscale network, you need for multiscale 1 only iteration at the very beginning. It was just the initial state which were quite difficult. So the few iteration solvers that were difficult. So there you need, like, let's say 50 or between 50 and 100 of iteration of Jacobi solver. But as soon as it's gone, like you see, it's almost 0 iteration of the solver. So that's why we have something that efficient. It's just to help some difficult part of the flow, and then the neural network is doing almost the rest itself. And when you reduce the number of parameters that you have in the multiscale network, of course, the multiscale network go faster, but it also makes larger errors. And as a result, you need more iteration in the hybridization. This is what you see here is no more new. Like all along the simulation, you need to still compute some Jacobi iterations. And so it reduces the effectiveness of the method. And this is the results in terms of elapsed time versus multiscale. We have done the same strategy with hybridization on 3D cases. So it's the same plum cases. I don't remember exactly the Richardson number, but you have the Jacobi methods on the top, the UNet, which is here not without hybridization. And on the bottom, you have the hybrid solver with CFD and the UNet working together. So it's no more a multiscale now. And you can see that we are able to compensate the small errors, like the small asymmetries of the flow. And again, if you go to a larger Richardson number, you need this hybridization to have something consistent with physics and still very fast.
Yeah, Michael, we are running a bit short on time, so
yeah.
No, I think it's just so that we can have a bit of a discussion, I guess. I mean, unless there's some critical.
I have done most of what I wanted to talk. Then it was just another application. You see, it was just on one command to have exactly the same kind of results.
Okay. Okay. Then yeah, I would like to see if there's any questions.